I'll start my presentation. Hello, my name is Gyuil Han, and I develop the SeriesOn servers at NAVER Webtoon. I believe that many teams are migrating the old legacy services to MSA. I'm going to share an example of how we came to develop faster and easier as we converted from the old monolithic-based SeriesOn legacy service to MSA structure. So if we work it harder, make it better, do it faster, wouldn't it make us stronger? That was the idea behind what we did, and that quote is, of course, the title of a Daft Punk song. For this session, I'm going to focus on how we used Armeria, GraphQL, gRPC, and Zipkin to migrate the services quickly and well. First of all, I'm going to briefly introduce what the SeriesOn service is. Next, I'm going to talk about how you can build quickly using Armeria. Then we'll ask the question, why is it better to use GraphQL? Followed by a talk on how we monitor the service. SeriesOn is an OTT media service of NAVER Webtoon. Its function includes purchasing a movie and watching it by streaming or downloading it in Korea. The image on the left is the mobile app version, and the one on the right is the TV app that has been newly released. As is the nature of a video service, various clients are currently offered, including TV and mobile app web player and window player. To give you a brief description of how this service was in the past, because it was maintained by a small number of people in the past few years, it was a monolithic and SQL-driven service, making it hard to expand and modify. So we thought about how to make the existing service lighter and migrate it faster in line with the passing of the times. As a result, the team came up with the following design for the structure, which was different from the existing structure. We divided the structure into client, front API service, backend microservice, and aggregation service, which will aggregate and deliver the backend microservice. The front API service manages the client-specific authentication and API invocations. With aggregation services, the backend services do not get directly called by the clients, but rather through the aggregator. So it checks what data is required using the front API service and aggregates individual data. In the case of the backend services, each component in the backend is responsible for multiple business logic such as authorization, contents to be played, payment, and movie metadata, and so on. So these were the things that we thought were important to consider based on what we designed while transitioning to MSA. First is supporting asynchronicity. Second is supporting distributed tracing to minimize monitoring problems due to an increase in structural complexity. Third is making sure it is light and fast. Fourth is generating a fast API auto documentation. These were the requirements. We carried out many researches to find a way that satisfies the aforementioned 4 requirements. So now I will tell you about how we quickly develop a component by applying Armeria. Armeria is an open source software that is powered by Line. As of the date of the presentation, the release version is version 1.12.0. Armeria is a microservice framework. It supports gRPC and Kotlin, reactive streams and coroutine for the asynchronous, and also Spring, which is familiar with Java web development. On top of that, as you see from the image on the right side, other features that make Armeria attractive is that it supports HTTP2, metrics, circuit breaker, and distributed tracing through metrics and Zipkin integration. Also, when we had a problem or a question compared to other open sources, the active support provided by the technical support team via Slack or GitHub was another aspect that made Armeria attractive. So our team decided to implement Armeria to build components, and after some reference research, we decided to develop it in combination with Kotlin, coroutine, gRPC, and Spring DI. As an advantage of Armeria, Kotlin actively supports the existing Java-based web framework. And because the experience was not far from the experience of developing the existing Kotlin-based Spring, it could be more naturally implemented into the team. The existing problem of gRPC was that it does not support browser call and that testing and debugging are difficult. gRPC does support gRPC web version as an extra, but it requires a cumbersome task of having to handle additional ports, which was one of its many problems. Fortunately, unlike the native gRPC server, Armeria supports various MIME types with a single port. The response value is automatically converted according to the requested MIME time, eliminating an aspect that has to be considered. Also, because it supports automatic documenting and testing based on protobuf, it is very useful not only when it comes to the actual testing, but also when sharing the test environment. As you can see on the right, because it automatically creates a protobuf-based interface and documentation for web tests just by clearly identifying the parameters, documenting time for individual component is greatly reduced within the team. Additionally, similar to Spring Swagger experience, Armeria supports an interface where header, query strong, body, and so on are passed on for testing. So gRPC testing has become very easy to carry out just by using JSON body without using RPC client like Bloom RPC. Also, in order to build faster using Armeria, we applied a boilerplate as the cornerstone. By creating components as quick as a flash and providing a speedy development environment, one big advantage is that business logic can be developed at the same time as component creation. Inside of the boilerplate, we combine the teams and the company's common library and Gradle setting and Helm charts so that the projects can be initialized faster. As you see on this page, by creating Armeria, Spring Boot 2, gRPC, Zipkin, and other dependencies to the Gradle-based project, and also by adding ELK stack for checking gRPC access log from Helm chart, we try to commonize the structures. By applying gRPC with Armeria, because most of the elements that have to be considered during a migration to MSA are supported and included in Armeria, building can be done faster and time can be saved through automatic documentation. And based on these aspects, we are also gradually migrating the current Spring-based REST API to Armeria. Also, by applying boilerplate within the team, we are able to accumulate and solve errors or problems that may occur later while managing the specifications within the team as a single template without having to go through any confusion with project settings anymore, which is a great plus. In the first half of the session, I talked about how to build components fast by using Armeria. And now I will talk about how we used GraphQL to aggregate and provide the microservice APIs. We first discussed a lot about how we are going to provide the client API ahead of the API development. The REST API and GraphQL were hot topics of discussion. You might have received similar requests as the ones shown on the slide while developing for a service. Some request that they need meta information in API A, or they request to include the coupon information in API B. As a result, we decided to choose a structure that would make it easier to respond to various clients. And we concluded that GraphQL, which supports various clients more flexibly, is the most suitable for our service. Most existing GQL services work like the image on the right. The client directly uses the GraphQL schema to call. The first benefit of this method is that because only the necessary response value is called from the individual clients through the schema, if GraphQL is well implemented on the server side, a flexible response is possible. However, if we opened up GraphQL directly, we figured that it would become more and more difficult to debug and track and manage the versions of the schema. So instead of putting the GraphQL in the front, we added a front API service layer that can handle authentications and queries like a gateway, and we tried to configure it so that the GraphQL would work like a data aggregator. So for example, if I'm retrieving my purchase history from the TV would call a REST format API named version 1 libraries. When that happens, the TV service will send a GraphQL query according to the schema, and when the permission and product metadata are called, the GraphQL would use the data loader to call each component to aggregate the data. This way, the client can retrieve all the data it needs to display on the screen with a single library API call, and because all of this is processed asynchronously in the server, the SQL-driven queries that took a long time to retrieve are now well separated and more easily retrieved. Of course, querying may be different for each client, but all of them can receive only the response value they need. If GraphQL is implemented without enough consideration, it can turn into a scary service with an okay front but connections looking like a spiderweb in the back. But by implementing the front API service layer, we are able to do versioning of GraphQL query. The history management for each client can be done more easily. Also, because both of the strength of GraphQL and REST API form of API can be utilized, management is easier, and because the N+1 issue can be sophisticatedly solved by using GraphQL, I think that is another point in favor of this structure. We are also able to benefit from the fact that the more accumulation in the data loader, the faster development speed will be within the team. For the next part, I will talk about how monitoring is done for the MSA structure that we have built. The first thing we considered in the team was that access logs should be managed by components. Second, we thought about distributed tracing and monitoring. And third, we thought that tracing and alarm will be needed for exceptions. Based on what we considered, I will first talk about how access log is gathered for SeriesOn. Each component runs on the Internet Kubernetes cluster. When the component is deployed, Armeria app, FileBeat, and logs are bundled as one pod and deployed to the Kubernetes pool through the Helm chart. The access logs generated at this time are collected into a single storage in Elastic Search. So by storing the access logs of all servers to Elasticsearch, archiving and querying by component and API becomes easier. Next, I'm going to explain how Zipkin is used for distributed tracing. Zipkin integration is provided by Armeria, so implementation of tracing can be done with the use of few lines of codes. And all components could be applied with Zipkin via Sleuth or Brave, which we thought was a great benefit. Also, server could easily be set up using the Zipkin server and Zipkin UI, and the backend storage could be uploaded to the Kubernetes network in 5 minutes using Elasticsearch. And by storing in the common Elasticsearch storage with the access logs, a more flexible search of the logs was made possible. So it has become possible to search by span name, service name, or tag query in Zipkin, and it has also become possible to trace which service called the API and what query was called. Also, by setting up a dashboard based on the data that are stored, monitoring by API has become possible. And error tracing and alarming have become easier to accomplish. Last part is something I also had a lot of difficulty with as we were implementing distributed tracing in an asynchronous environment. So I would like to talk about one thing that needs to be handled carefully during development. In an asynchronous environment, because there is no guarantee that a request is from the same thread, therefore tracing context must be well managed so that it is not lost. This might be difficult to understand, so I will explain it in the next slide. Let's take a look at this example. When the TV service calls a library API, it retrieves the response value through several micro API hops. At this time, if each component is individually called asynchronously by GraphQL, the calls can be made through multiple thread pools. If the parent span is delivered normally to these multiple threads, it will be traceable and the result will look something like the figure on the bottom. However, if each call is from a different thread, the trace context is misdelivered or lost and it becomes untraceable. And there is the risk that each request will be treated as different requests or mixed with requests invoked by other users. To solve this problem, when the call is from another thread pool, what you can do is explicitly call subscribe on and change it to make it run on a specified scheduler or context, then pass the trace context. The same situation can occur in coroutine. This situation can be solved like reactive subscribe on by injecting a coroutine context. And starting from the recent version of Armeria, Kotlin gRPC automatically supports context injection. Now we are in the final part of the structure. The request that went through the API gateway goes through each front API and requests the required data through GraphQL, and the GraphQL calls and aggregates the backend layer through the gRPC. The error logs requested at this time are collected through the in-house system Nello, and the gRPC access log is collected through the ELK stack. Each span data for distributed tracing are stored in Elastic Search through Zipkin, and finally, these data can be visualized and seen on Kibana. Of course, we could have made it better by using Kubernetes-based ISTIO or Spring Cloud ecosystem. But we actively implemented Armeria, gRPC, Zipkin, GraphQL within the team to reduce items to consider and to quickly focus on the development of business logic. Migrating a legacy service with old structures to MSA is a very difficult task. If we stopped serving a service and created a completely new one, then we could have adopted the most ideal changes, but that is quite unrealistic, and our timeline is always very tight. By implementing Armeria and boilerplate, we could accomplish a faster project setup and development, and we increased the usability of gRPC, making testing easier. Also, through a faster data aggregation via GraphQL, the service became more flexible. And with the support of distributed tracing via Armeria, I think we were able to make the transition to MSA faster. It is not in the final stage yet, but I look forward to the future of the SeriesOn server that will become better and better in the future. Thank you.